Hi, everyone. Our last lab in the class is going to be about nonlinear optics. So once again, this is a subject that isn't a normal part of the curriculum of this class. It kind of goes beyond the things that you're learning. But it's really interesting and it's important as well. And we have some neat experiments that you can do that probe some aspects of nonlinear optics. So uh, I'd like to start by giving you some background uh, in this subject so you can understand the experiments that you're going to do. Okay? Here, hang on for a moment. Okay, this is an outline of what I'd like to cover. We'll probably break this into a couple videos. But in any event, we're going to get an introduction to nonlinear optics. I'd like to start by just reminding you about linear optics, the thing that we presumably are familiar with. And what we found there is that starting from the idea that materials have an electric susceptibility, we can figure out what their dielectric constant is and their index of refraction, and then talk about things like reflection and transmission and Snell's law. Linear optics. When we go to talk about nonlinear optics, we'll start by describing nonlinear polarization, okay? And we'll see that in general, the polarization is a function of the electric field, but maybe not a linear function. However, often we can express it as a power series in electric field. Okay? And that'll lead us to talking about nonlinear optical phenomena of different orders associated with the terms in this power series expansion. Well, you'll see what we mean in a few minutes. So we'll talk about second order phenomena and then third order phenomena. Second order phenomena include a lot of really interesting things, including frequency doubling or second harmonic generation, as well as a related phenomena called optical rectification. It includes sum and difference frequency mixing. Something called the electro-optic effect. And then, at least in my description here, this includes a somewhat related phenomenon called Raman scattering. Although Raman scattering actually is a little bit different than the other nonlinear phenomena. We'll also talk about some third order nonlinear phenomena, actually just one, something called the Kerr effect. Well, so far I've just thrown a bunch of names at you. I haven't told you what any of these things are, but I do want to just give you an outline of where we're going to go so that when these names come up again, you'll think, aha, I've heard that before. Okay, hang on one more moment. Okay, let's start our discussion by thinking once again about linear optics, the familiar topic we've been studying. And we want to think about a material that maybe is made up of atoms. So here's an atom. Under normal conditions, it has no dipole moment. It's spherically symmetric. But if we place it into an electric field, then it can polarize, which I'll enormously exaggerate here in my cartoon picture. So if I place the atom into an electric field, then it can polarize, which means that the average position of the positive charge and the average position of the negative charge are pulled apart. Like so, okay? And so now it gets a dipole moment. And the dipole moment of the atom, we have said, is usually proportional to the electric field. So it's equal to a constant, proportionality, polarizability, times the electric field. And this is the basis of linear optics. Then, for a material made up of these atoms, we can say that the density of dipole moment, or the polarization, will be given by a constant times the electric field. So here the constant is the dielectric susceptibility, chi, and then multiplied by E0, which is just there to make the units work out. Okay? But notice that this is a linear equation. The polarization is just proportional to the electric field. Oh, excuse me. And from this, we get a lot of familiar results. We can find that the dielectric constant of the material is just 1 plus the electric susceptibility. And then we find that the index of refraction in a non-magnetic material is just the square root of the dielectric constant, and we're off and ready to go. Okay? And then we can think about light that interacts with some material, and we find that we can describe everything that happens in terms of the index of refraction in linear optics. So light strikes our material, some of it bounces off, some of it is transmitted, and we can describe the reflection. Sorry about my cartoon picture. We can describe the reflection, we can describe the transmission, we can describe Snell's law. All of these things can be described using linear optics. So reflection, transmission, and so on. If this is a lossy material, it would have absorption. Oh, how nice. Excuse me 1 second. All of these phenomena are described in linear optics. And there's an important consequence that we should keep in mind. If the response is linear, then the frequency of the reflected and transmitted light is always equal to the frequency of the incident light. So the frequency doesn't change. And it's simply related to this, that if the electric field is oscillating at some frequency, then because the polarization is proportional to field, it will oscillate at the same frequency. And then the oscillating polarization is actually the source for the reflected wave and the transmitted wave. Very good. Now, let's see what happens when we introduce nonlinear polarization. Okay, we can expect that if we make the electric field strong enough, that the polarization will not stay strictly proportional to electric field. For example, you might imagine you make a sketch of polarization versus field, or dipole moment versus field for an atom, that if we make the electric field stronger and stronger and stronger, eventually this is going to diverge from a straight line, and then at some point the atom will actually become ionized. And the electron and the proton will be pulled apart. Well, before we get to ionization, we certainly expect that the dipole moment of the atom will stop being proportional to the electric field. So the linear response breaks down at strong fields. But for fields that are not too strong, we can still usefully write the polarization in terms of the electric field, in terms of a power series. So we can say that the polarization is equal to a constant, epsilon naught, times the susceptibility times the electric field, plus another constant called the second order susceptibility, or chi2, times the electric field squared, plus, oops, I have to go down to the next line, plus another constant, we'll call it the third order susceptibility, times the electric field Q, plus, and our power series can go on as far as we want. Now, this power series expansion is very useful, and it's useful in the normal case, where the electric field is strong enough that these terms are important, but it's weak enough that each term gets smaller than the previous one. So the polarization due to the second order term, let's say, is weaker than the polarization due to the first order term. And the third order polarization is weaker than the second order polarization. And we'll see that's reasonable, but for all but the most ridiculously large fields, okay? Something that we should note, though, is that there are cases when, for symmetry reasons, the second order susceptibility will be 0. And this is true in what are called centrosymmetric materials. So, for example, silicon would be a centrosymmetric material. If you take a silicon crystal and you turn it upside down, it looks exactly the same. It's centrosymmetric, okay? So silicon is a crystalline material with that form. I'm sorry, something crazy happened here. Give me 1 second. There we are. But also non-crystalline materials. Are typically, on average, they're centrosymmetric. So they also have no effective chi2. In those cases, then chi3 is very important because it's the first correction to the linear response. Okay, but we want to think in terms of this power series expansion. Okay. Here, let's just talk about an actual material. We'll set it up here and then I'll ask you a reading question about it, okay? So there's a crystalline material called ADP. It's NH4 H2. Oh no, I've run out of space. I've got to write it on the next line. There it is. It's a crystalline material that's often used for nonlinear optics because it has an especially large second order nonlinear susceptibility, okay? For this material, the electric susceptibility, the linear susceptibility is 1.25. And the second order susceptibility, which I'm writing as chi2, not chi squared, just chi2, second order susceptibility, is 1.5 times 10 to the minus 12. Okay? The susceptibility doesn't have any units, and the second order susceptibility has units of 1 over electric field. Okay? So let's figure out the electric field required to make to make the polarization due to the second order field just 1% of the polarization due to the linear term. So the polarization due to the second order term over the polarization due to the first order term, we'd like that to be equal to 1%, okay? Now, of course, the polarization due to the linear term is just epsilon naught times the susceptibility times the electric field. And the polarization due to the second order term is epsilon naught chi 2 times the electric field squared. This is going to be equal to 0.01. And what I'd like you to do is to find the electric field that makes that true. And it should be kind of large. But hang on, and a reading question will pop up. Okay, did you find it? You should have found that the electric field required is about 8 times 10 to the 9th volts per meter. 8 billion volts per meter. This is a very, very strong electric field. It's of the order of the strength of the electric field inside of an atom. That's the scale that you need before these higher order terms become very important, okay? And so that's why it's usually safe to assume that in this power series expansion, that the terms get smaller as we go to higher and higher order. Very good. By the way, once we found the electric field, we can find the intensity. Okay? The intensity for light traveling through a material is given by 1/2 epsilon naught times the index of refraction times C times the electric field squared, where the index of refraction, remember, is just the linear susceptibility plus 1. So go ahead now and figure out what the intensity of light is, has to be that would produce this magnitude electric field, and thus produce 1% second order polarization compared to linear polarization. You should find that the intensity is a staggeringly high, excuse me, um, it's about 1 times 10 to the 17 watts per meter squared. Okay, that's pretty high, right? It's 10 million times the intensity of, I'm sorry, it's extremely high. The analogy escaped me. Oh, compared to sunlight, 10 to the 15 times the intensity of sunlight. No, 10 to the 14 times. Okay, there we go. All right, so nonlinear optical phenomena are produced by nonlinear polarization, okay? In strong electric fields, we have to worry about nonlinear corrections to the polarization. And we can expand the polarization in terms of the electric field, as is shown here. But these corrections are only important for very strong electric fields. All right, let's stop there and we'll take this up in the next video.